Hello everybody, and welcome to our video on maximum and minimum values. So we're going to start out with a definition. A function of two variables has a local maximum at AB if the value of the function at xy is less than or equal to f of AB whenever xy is near AB. The number f of AB is then called a local maximum value. If, on the other hand, f of xy is greater than or equal to f of ab when xy is near ab, then f of ab is called a local minimum value. If the above inequalities hold for all points xy in the domain of f, then f has an absolute maximum or an absolute minimum at ab. Obviously, we change the terminology depending on which of these two conditions is satisfied. Okay, so a theorem. Now, you've seen a theorem just like this from Calculus 1, but this was obviously extended into this three-dimensional realm we're working in now. So if f has a local maximum or minimum at ab, and the first-order partial derivatives of f exist there, then the partial derivative of f with respect to x at ab is 0, and the partial derivative of f at y, or with respect to y at ab, is 0. So this is very similar to your theorem in 2D that says, hey, if you've got a peak, right, then the slope at that peak is 0. But here, we're working in 3 dimensions, so we're checking both the partial derivative with respect to x and with respect to y. But let's just pay close attention to the order of this theorem. This theorem says if f has a local maximum or minimum, then its partial derivatives are 0. But not the other way around. You might have that the partial derivatives are 0, and there might not be a local maximum or minimum, so just keep that in mind. All right, definition. A point AB is called a critical point of f if the partial derivative with respect to x and y are both 0, or one of those partial derivatives does not exist. Okay, so example 1, find the local minimum and absolute minimum for f of xy. So we're going to start by finding a critical point here. So the partial derivative with respect to x is 2x minus 2. So 2x, this is 0, minus 2, 0 and 0. Partial derivative with respect to y is 2y minus 6. That's going to be 0, that's going to be 0, and that's 0, and then we get 2y and minus 6 here. So if the partial derivative with respect to x is 0, that implies x equals 1. And here, if the partial derivative with respect to y is 0, that implies y equals 3. So in other words, 1, 3 is a critical point. But this just tells us where it's possible that there's a maximum or minimum value. Again, it doesn't say that this is a maximum or minimum value. Okay, so how can we actually show that there's a maximum or minimum value there? Well, that depends on the function that you're analyzing. In this case, this function can be rewritten in a way that's going to be helpful. So if you notice, you've got this x squared minus 2x and y squared minus 6y. Looks kind of like quadratics involving x and y. And so I'm actually going to take those quadratics and complete the square with each of them. So that'll let us rewrite this in a way that'll be pretty helpful here. All right, so all I've done here is reorganize this with my x terms first, then my y terms. And then I've left a gap of 2 spaces for each of these quadratics for completing the square. So as always, we complete the square by adding 1/2 of b. b here is 2, so 1/2 of that is 1, and squaring it, and then subtracting the same thing. So here b is 6, so 1/2 of that is 3 squared, and subtract it, which is 9, so I'll just write 9 there. So now we're going to factor each of these expressions. This gives us x minus 1 squared. Here is going to give us y minus 3 squared. Here we've got -1, -9, that's -10 plus 14, so that's plus 4. And what do we notice? Well, we notice, hopefully, that x and y correspond to these values here. What makes these 0? So both of these expressions are strictly greater than or equal to 0, which means that the value for x equal to 1 and y equal to 3 corresponds to a minimum value here. So, in other words, f of 1, 3, which is equal to 4, is an absolute minimum for the function. All right, that's it for example 1. Let's go ahead and move on. So here for example 2, find the extreme values of f of xy equals y squared minus x squared. So the partial derivative with respect to x here is -2x, and with respect to y is 2y. So these partial derivatives being 0 imply that x equals 0 and that y equals 0. So 0, 0 is the only critical point. Okay, but now we've got to see, is there actually a maximum or minimum here? Well, consider, if I fix x equal to 0, but y is not equal to 0, what do I get for my function? Well, y squared will always be positive. Minus 0 gives me a positive value, so that tells me that f of xy will be strictly positive if x is 0 but y is not. And if y is 0 but x is not, then that implies that this function is negative, since you'll have 0 minus a positive number. So what that tells us is that near 0, 0, you get both values larger than 0 and smaller than 0, which tells you the function is neither strictly larger or strictly less than the value at that point. So this implies that f of x, y, has no extreme values. Right? The only possible place it could have had an extreme value is at the critical point, and at this critical point, the function takes values both larger and less than the corresponding function value right at that point. So, all right, let's go ahead and move on to the second derivative test. So, obviously, in the first two examples, we dealt with very particular functions and had to use the very specific properties of those functions to figure out what and if there were extrema. So we'd like a more general tool. So this isn't going to cover all cases, but the second derivative test is pretty powerful. It's going to let us cover a lot of situations. So suppose that the second partial derivatives of f are continuous on a disk with center AB. And suppose that the first partial derivative with respect to x equals 0 at AB, and the first partial derivative with respect to y equals 0 at AB. So in other words, AB is a critical point. Let D be equal to the second partial derivative times the first partial derivative times, let me try that again. The second partial derivative with respect to x times the second partial derivative with respect to y minus the partial derivative of f with respect to x then y squared, all evaluated at AB. So this is our value D. If D is positive and the second derivative with respect to x is positive, then f of AB is a local minimum. If D is positive and the second derivative with respect to x is negative, then f of AB is a local maximum. If D is less than 0, then f of AB is not a local maximum or minimum. Okay, so there's a whole lot of moving pictures here, but it's actually very similar to the second derivative test from Calculus 1. So that test basically says, hey, if you've got a second derivative, if f double prime is positive, that tells you that your graph is curling upwards near the point. And so that tells you that this is a local minimum, right? And on the other hand, if the second derivative was negative, that would tell you you had a local maximum because you'd have something that looks like this. So here we've got kind of a lot more pieces because we have 3 dimensions to worry about, right? So the first thing is what does the second derivative here with respect to x tell us? Well, if it's positive, then f of ab is a local minimum. But this is only if the condition d is met. So let's just kind of ignore that condition and just think about this at a basic level. This tells us that at least in the x direction, that the graph is curling upwards from the point. So this point is a local minimum. And if this second derivative with respect to x was negative, then at least in the x direction, the graph is curling downwards. And so this is a local maximum. But it's not enough to just consider the x direction. All right, so that's why we have this extra condition d. So let's think about the pieces here. First, for d to be positive, that necessitates immediately that either both of these second partial derivatives are positive or both are negative. Because this term here is minus a squared number, it's going to be strictly a negative result here. So we at least need this to be positive for d to be positive. So that's the first condition. So that tells you, what does it tell you? It tells you both of these second partial derivatives are either positive or both are negative. So in the x and y directions, the graph either curls up in both directions or down in both directions. So then if we know that they go in the same direction, then it's enough to check just one of them to conclude whether it's a local minimum or maximum. Now, that's a pretty good start, but we have this extra condition, this extra piece of d here. So the partial derivative with respect to x first, then y. So you can sort of think of this like the twist, right? Because you're looking at the first partial derivative with respect to x. So that's telling you the rate of change of the function in the x direction. And then the second partial derivative tells you that if you move in a y direction from that, how much curl are you getting? So you can sort of think of this like telling you how much the function is twisting towards the x equals y lines. So let's just take a look at this graph here. So when d is negative, so when either these don't match, the second partial derivatives for x and y, or this is just much larger values, so it makes the whole thing negative. So if you get that d is negative, then f of ab is not a local maximum or minimum. And that looks like this situation here, which we call this case a saddle point. Because, it usually looks something like this. So if you see at 0, 0 here, you've got along the y direction, you've got the graph curling upwards. And along the x direction, you've got the graph curling downwards. So d is going to be negative here. And you end up in a situation where you don't have a local maximum or a local minimum at that point. Now, an extra note here is that if d is equal to 0, the test gives no information. So you can't conclude anything, and you're going to have to take some other sort of approach, like we did in this first problem, maybe. Completing the square is the kind of approach you could take there. But yeah, that only happens if d is 0. If d is not 0, then you can go ahead and use the second derivative test. And a last little note here is that this d could be written in this discriminant notation. So the second partial derivative with respect to x, then xy, then yx, then yy, equals this minus this partial derivative with respect to x, then y squared. Now, you might ask yourself, why can we just write that this is f with a partial derivative with respect to x, then y squared, when you're really taking this product here? Well, that's because this condition says the second partial derivatives are continuous. And we had a theorem from before, Clairaut's theorem, that says that if the second partial derivatives are continuous, then they are equal. So we're relying on that condition here. Okay, so with that out of the way, let's actually try to apply this. So let's take a look at an example. Find the local, minimum, maximum, and saddle points for the function. So first we've got to start by finding any critical points. So the partial derivative with respect to x gives me y minus 2 minus 2x. And the partial derivative with respect to y gives me x minus 2 minus 2y. So now if I set this first partial derivative equal to 0, I get 0 equals this whole thing, and I can rewrite that as y equals 2 plus 2x. And here, if I take the partial derivative and set it equal to 0, we get x equals 2 plus 2y. And we're just going to substitute in this value for y. 2 plus 2 times 2 plus 2x. That's going to be 2 plus 4 is 6 plus 4x. So x equals 6 plus 4x, which implies negative 6 equals 3x, which implies x equals negative 2. And that implies y equals, well, if x is negative 2, that's 2 minus 4, so that's negative 2 as well. So negative 2 is the critical point. Okay, so now we need our partial derivatives. So the second partial derivative with respect to x, I look at the first one, I get negative 2. The second partial derivative with respect to y is going to give me negative 2. Partial derivative with respect to x, then y. So I look at this, now I take the derivative with respect to y, I get 1. And we got to make sure that these are both continuous, though. That's the condition, continuous and or equal. So what do we get here? When we take the partial derivative of y with respect to x, we get 1. So these are both equal, perfect. So now we can calculate d. So it's the second partial derivatives with respect to x and then with respect to y minus that partial derivative squared. And now I technically need to evaluate this at the point, but since these are all constant values, that doesn't make a difference here. So this is negative 2 times negative 2 minus 1 squared. So this is 4 minus 1, which is 3. So d is positive. And what else do we know? We know that the second partial derivative with respect to x is negative. So if d is positive and the second partial derivative is negative, then that tells us this point corresponds to an absolute maximum. So let's plug these values in. We get 4 plus 4 plus 4, that's 12, minus 4 minus 4, so it's minus 8. So 12 minus 8 is 4, is an absolute maximum. Now we know it's an absolute maximum because it's a local maximum and there are no other critical points. So there's no other possible maximums. So this has got to be the largest one. Or actually, sorry, that's not quite true. That would be if we were on a bounded region. So that's not necessarily the case. So let's just not say that without extra conditions. I don't want to go too far. Let's just say it's a local maximum. Now, that's different than our first function where we knew we had an absolute maximum because this thing was strictly greater than or equal to 0 in both cases. So we could say for sure that this was an absolute minimum here. Okay, so that's it for example 3. Let's take a look at another example. Find the point on the plane, x minus 2y plus 3z equal to 6, that is closest to the point 0, 1, 1. Okay, this seems pretty tricky, but really what this is asking us to do is to minimize distance. And, well, then we need to look at our distance formula. So distance formula should be the square root of x minus a squared plus y minus b squared plus z minus c squared. But this is actually kind of rough because we're going to have to take a bunch of partial derivatives, and the square root's going to really complicate them. But since distance is a positive value, then instead we can worry about minimizing the distance squared, because whatever minimizes the distance squared is also going to minimize the distance, right? So that doesn't make a difference here. Okay, so we'll use d squared as our function, and we've got our point. Our point is 0, 1, 1, so this is x squared plus y minus 1 squared plus z minus 1 squared. But this is also a problem because we have 3 variables here, and our approach relies on having 2 variables. Whatever will we do? Well, we do have a constraint, right? That's the key piece of information we can get from this equation from the plane. So we can rewrite this as z equals and substitute in place of z. So let's go ahead and do that. So our plane equation gives us 3z equals 6 minus x plus 2y. So that implies z equals 2 minus x over 3 plus 2y over 3. And so if we just substitute that into our equation for d squared, two minus x over 3 plus 2y over 3 squared. Okay, and now we could multiply all this out before taking our derivatives, but keep in mind this is going to be a real mess to multiply out, so it's actually going to be easier to just use the chain rule on this portion anyways. So that's what I'm going to do. I'm just going to use the chain rule here. So we'll take the derivative with respect to x. We get 2x. This will be 0 plus 2 times this expression to the first power times the derivative of the inside of this function, which is just negative 1/3 in terms of x. So this is 2x plus 4 minus 2x over 3 plus 4x or 4y over 3, I should say. But these are all multiplied by negative 1/3. So this becomes 2x minus 4/3 plus 2x over 9 minus 4y over 9. And finally, that's going to give us, so 2x plus 2x over 9, that's going to be 20x over 9. And then minus 4y over 9 minus 4/3. Okay, that's the partial derivative with respect to x. Now we got to do the same thing for y. Okay, so this first derivative will be 0. And then we'll get 2 times y minus 1. And then the derivative of the inside function here is just 1 in terms of y. Plus, now we got to use the chain rule again. 2 times the inside times the derivative of that inside with respect to y, which is just 2/3. So this gives us 2y minus 2 plus, and now I'm just going to treat this as 4/3. So 4/3 times 2 is 8/3. And then 4/3 times this gives us 4x over 9. And then 4/3 times this gives us 8y over 9. Okay, so 2y plus 8y over 9 is going to give us 26y over 9. And then we've got negative 4x over 9. And then we've got 8/3 minus 2. So that's minus 6/3, so that leaves us with a positive 2/3. Okay, so next step here is to set each of these things equal to 0 and solve away. So if I set my derivative with respect to x equal to 0, we get 0 equals 20x over 9 minus 4y over 9 minus 4/3. So I'm going to add this 4/9 of y across. And I'm going to give this a common denominator. So instead of minus 4/3, I'm going to make it minus 12/9. So now I can multiply 9 across, and those will cancel. And then I can divide by 4. This gives me y equals 20x minus 12 over 4, which is 5x minus 3. So that's not too bad. That worked out kind of nicely. Now we'll take this result and we'll plug it into what we get for d squared with respect to y equal to 0. So 0 equals 26y over 9 minus 4x over 9 plus 2/3. Okay, so 26 times 5, that's 130. X over 9 minus 26 times 3, which is 78 over 9, minus 4x over 9, plus, and then I'll give this a common denominator too. We'll make this 6 over 9. So we get 130 minus 4, that's 126x over 9. And then negative 78 plus 6, that's going to be negative 72 over 9. Okay, so 126 divided by 9. Well, 126 is divisible by 9. And what is it? It's 14 minus 8. So 0 equals 14x minus 8. Move the 8 across, divide by 14, and we get x equals 4/7. And if x equals 4/7, that implies that y equals 5 times 4 over 7 minus 3. That's 20/7 minus 3. And 3 is 21 over 7, so this is negative 1/7. So altogether, that tells us that 4/7 and negative 1/7 is a critical point. Now, we might be tempted to apply our second derivative test here, but this is a perfect example of a problem where that's not necessary. Because if we think about the problem, we're trying to find the point, the shortest distance, or the point on the plane corresponding to the shortest distance. But we know that that's always the perpendicular distance, and any other distance from this point, which, what was the point we were given? 0, 1, 1. This is 0, 1, 1. Any other point on the plane will always be a longer distance away. So that means this problem can only have a minimization result. You can only minimize this distance. You can't maximize it. So that means this critical point corresponds to the minimum distance, period. So now all we gotta do is find the closest point. So we have our equation, x minus 2y plus 3z equals 6. And now if we plug in our critical point, we get 4/7 plus 2/7 plus 3z equals 6. This is 6/7, and we're going to subtract it. So this gives us 3z equals 6 minus 6/7. 6 times 7 is 42, so this is 42/7 minus 6/7. That's 36/7. So 3z equals 36 over 7. And now if I divide by 3, I get z equals 12 over 7. So the point that is closest on the plane is 4/7, negative 1/7, 12/7. All right, well, that's it for this example. Hopefully that was fairly clear. Let's go ahead and move on to another problem. A rectangular box without a lid is made from 12 meters squared of cardboard. Find the maximum volume. So, well, let's draw a little picture here. Kind of make sure what's going on is pretty clear. So you got a box. Not particularly well drawn. We'll call this x, this y, and the height z. So then we know that the volume is just x times y times z. But what else do we know? Well, we know that if we were to lay this out in a net diagram, so if you just imagine cutting along each diagonal of this box and folding the sides outwards, then it would look like something like this laying on the floor. All right, so this net diagram is going to give us the area of our cardboard that's used to make our box, right? So we got x and y coordinates here, y and z on the sides, and then x and z on these sides. So the area is going to be x times y times z, y times z, x times z, and x times z. So in other words, we know that the total of these 5 areas is equal to x times y plus 2x times z plus 2y times z. And this is important because what we want to maximize is volume, but we have 3 variables here, so we need to use this constraint to remove our variable z here, so we can get this to just 2 variables. So what we're going to do here is just subtract the xy, and then factor out z, and then divide that term, so we get z equals 12 minus xy divided by 2x plus 2y. And we plug that into our volume formula, and we get xy times 12 minus xy over 2x plus 2y. So if we distribute this into the numerator, we get 12xy minus x squared y squared divided by 2 times x plus y. Okay, so that's a start. Now we need to take a bunch of partial derivatives. So let's go ahead and do that. We'll take the partial derivative with respect to x. So we have to apply the quotient rule. So that's the derivative of the top times the bottom minus the top times the derivative of the bottom. Divided by that denominator squared. Okay. So remember, this derivative is with respect to x here. That's key. So this is going to give me 12y minus 2xy squared times 2x plus 2y minus 12xy minus x squared y squared times, well, the derivative of this with respect to x is just going to be 2. Actually, instead of writing this as 2x plus 2y, I'm going to leave that 2 factored out. And in the denominator here, I've got 4 times x plus y squared. So if we imagine factoring this 2 out of these 2 terms, we could cancel that factor with this here. So I'm going to kind of skip that a little bit. But that makes it a little easier to multiply this stuff, a little less messy. So now we've got to multiply 12y minus 2xy squared times x plus y. That's going to be 12yx minus 2x squared y squared minus 2... oops. Okay, so that was that term, and now we need 12y times y. So that'll be plus 12y squared, and this will be minus 2xy cubed minus 12xy plus x squared y squared, all over 2 times x plus y squared. Okay, so 12yx and negative 12xy cancel. Here we've got negative 2x squared y squared and positive 1x squared y squared. So we end up with just negative 1 of those things. So this is negative x squared y squared plus 12y squared minus 2xy cubed over 2 times x plus y squared. And then I'm just going to make one little extra adjustment here. I'm going to factor out a y squared up top. We'll see why that was important here in a bit. Okay, so that's it for the partial derivative with respect to x. Now we have to do the same thing with respect to y. So some of these problems do get a little cumbersome on the computation. There's not much we can do about that, but bear with me. So I'm going to kind of just write quickly here and not narrate everything, since this is basically the same steps here, but just keep in mind that our derivatives are with respect to y this time, not x. Oh, I should have canceled both of those factors of 2 there. All right, now that's fixed. So now we got to do this multiplication here. So we get what? 12x squared plus 12xy minus 2x cubed y minus 2x squared y squared. And then we've just got these two terms here, minus 12xy plus x squared y squared over 2 times x plus y squared. And again, we end up with these terms here that cancel. So we get a positive 12x squared minus 2x cubed y. Now we've got negative 2 of these and plus 1 of these, so that's just negative x squared y squared divided by 2 times x plus y squared. And now we can factor out an x squared up top. So this gives us x squared times 12 minus 2xy minus y squared over 2 times x plus y squared. Woo! All right. Well, computation's a little tedious on this one, I'll admit. But we've made some good progress here, right? We're pretty close to being able to deal with this problem. However, you might not think so if you look at these partial derivatives. You say, I need to set these equal to 0 and solve them. These seem pretty bad, and they're kind of rough. But this was the key to us noticing that we could factor out the y squared and the x squared terms here. That's going to be crucial. So if the partial derivative with respect to x is 0, what does that tell us? Well, this is a fraction. Fractions are only 0 when their numerators are 0. And we were able to factor this numerator into these two pieces. So that means one of these two things has to be 0. So either y squared is 0 or negative x squared plus 12 minus 2xy is 0. But y squared can't be 0 because then the volume would be equal to 0, which is absurd. Right? We're not maximizing volume if the volume is 0. So now we look at the partial derivative with respect to y and set it equal to 0, and we get a similar thing. We get that either x squared is 0 or 12 minus 2xy minus y squared is 0. So first of all, if x squared was 0, then the volume would be 0. That's absurd. We can ignore that one. And now here comes the next tricky piece. So as you can see, the algebra here, you got to kind of just be a little tricky here to solve some of these. Sometimes you got to rack the old noggin for a little while. But what do we notice? We got 12 minus 2xy and 12 minus 2xy. So these are both similar. The only difference is the negative x squared and negative y squared. So if I rewrite this as 12 minus 2xy equals x squared, and I do the same thing for this equation, I get 12 minus 2xy equals y squared, well then these two things are equal. So therefore, x squared has to be equal to y squared. And since we know x and y have to be positive, because we're talking about volume here and lengths, that means that they're both equal and positive. Okay, so we've got that x equals y, and we have a constraint equation up here, which I'm going to save myself a little effort and just copy here. I'm really running out of room, aren't I? Okay, so if we plug our x and y values into our constraint equation, and with z, so we know that z equals this. So let's actually do z first. So we'll write z in terms of x. So we've got z is 12 minus xy over 2x plus 2y. Yeah, I mean, we're actually using the same equation. It's just easier in this form. So we'll just do it like that. So what do we get? We get 12 minus x squared over 2x plus 2x. So that's 4x. Okay. That should be fine. We should be able to take that and just plug that into our volume equation. Or actually, wait, let's see. We need to... Bear with me 1 second here. All right, so we've got our critical points. And we've got our relationship between x and y. They're both equal to one another. Okay, so we need to plug those in. We found z in terms of x and y, or in terms of x. Okay, so now we'll plug back into the original constraint, and that should give us everything that we need to solve for x. So I actually did need to go ahead and copy that again anyways. Yeah, the problem's a little long. Lost my place. Here we go. Okay, so what does this give us here? This gives us 12 equals x squared plus 2x times 12 minus x squared over 4x plus 2x times 12 minus x squared over 4x. So this is x squared plus, so the x over x cancels in both cases, and 2 over 4 becomes 1 over 2. So since these fractions are both over 2, we'll just combine them together. 12 minus x squared plus 12 minus x squared all over 2. Okay, so this becomes x squared minus... we've got a minor error in here because those would cancel out, and that would give me just 12 equals 12, which is silly. All right, bear with me for a second. Let me just think about this one. I've clearly done some little silly mistake, so just gotta mull it over for a moment. Ah, I got it. Okay, let's back this up a little bit. Kind of skipped a little bit of a step in here. So I got x equals y. So what I need to do now is plug this into one of these equations and solve for one of those specific values. So I made things a little bit more complicated on myself than I needed to. So let's try this again. Okay, so we're just plugging in x equals y into this equation, replacing y with x. And so we get negative x squared plus 12 minus 2x squared equals 0. So this is negative 3x squared. I move that across and I get 3x squared equals 12. Divide by 3, I get 4, and hence x equals 2. And we know it's not the negative value because of the nature of the problem, right? So x is 2, and if x is 2, then y is 2. And if x and y are both 2, then z is 12 minus 4 over 8, which is 8 over 8, which is 1. So therefore, the volume equal to 2 times 2 times 1, which is 4, is the maximum volume. And again, this is another situation where the context of the problem tells us that we can only have a maximum here, not a minimum, because you could always flatten the box and still have 12 meters of material, even though your height is 0 and the volume is 0. All right, so let's move on to a couple quick definitions, and then we'll get to our last topic for this section. So, definition. A closed set in R2 is one that contains all of its boundary points. A boundary point of D is a point AB such that every disk with center AB contains both points in D and points not in D. So, in other words, the boundary points are the points on the edge, because if you take one of those boundary points and you draw a little circle around it, you get points both inside and outside your region. So, each of these has boundary points. The question here is, does the set contain all of its boundary points? So when we have a filled line, that means that curve is part of the boundary or part of the set D. So in this case, any of these points on the edge are included in this set D, and hence this set is closed. Same thing here. But the dotted lines indicate that those points, that curve is not included, and therefore this point, which is a boundary point, is not part of the set, and so the set is not closed. Now in this case, most of this curve is included, but we had a hole here, and at this boundary point, it was not included in the region D, so this is not closed. And here we've got 3 of the sides of the square are not included, so these boundary points are not in the set, and hence this is not closed. So hopefully that makes some sense. And another definition, a bounded set in R2 is one that is contained within some disk. So all that really says is a set is bounded if we can draw a circle around it. So pretty simple definition. Okay, so theorem, the extreme value theorem for functions of two variables. If f is continuous on a closed and bounded set in D in R2, then f attains an absolute maximum value and an absolute minimum value at some points x1, y1, and x2, y2 in D. So guide, to find the absolute maximum and minimum values of a continuous function f on a closed bounded set D, first you find the values of f at the critical points of f in D, and then you find the extreme values of f on the boundary of D. After that, once you have those values, the largest of those values is the absolute maximum, and the smallest is the absolute minimum. So, let's just kind of tackle a problem here, and that should help make this idea clear. Find the absolute maximum and minimum values of this function on the region D that is a closed triangle with vertices 2, 0, 0, 2, and 0, negative 2. So first, let's find the critical points for this function. We'll find the partial derivative with respect to x is 2x minus y, and with respect to y is 2y minus x. If we set these both equal to 0, we get that y equals 2x and x equals 2y. If we plug in the substitution for y, that gives me x equals 4 times x. Well, actually, the only possibility here is going to be that these are both 0, right? So if x equals, here we'd get 4x. So this is only true if x is 0. Which implies that y equals 0 as well. So 0, 0 is a critical point. And let's go ahead and just evaluate the value of the function there, which is just 0. So we'll keep that in mind. Now, we've dealt with our critical points. Now we have to deal with the boundary of our region. So let's try to draw that here. So this is 0, 2. This is 2, 0, and 0, negative 2. And so you get this triangle. And so we need to know what the curves are that are associated with each part of this triangle. So this first curve is the line y equals negative x plus 2. Right, that's got a slope of negative 1. It's got a y-intercept of 2. Done. And this curve is the line with slope of 1 and y-intercept negative 2. And this curve is the curve where x equals 0. So now what we're going to do is just take each curve, substitute it into our function, and it'll be a constraint on our function, and it's going to give us a function of only one variable now. So in the case of the first curve, we get a function of x squared plus negative x plus 2 squared minus x times negative x plus 2. This is x squared plus, and when I multiply this out, I get x squared minus 4x plus 4, and then here I get plus x squared and minus 2x. So this becomes 3x squared minus 6x plus 4. So now if I want to find a maximum or minimum on this function, I just take my calculus 1 approach, right? Which is take the derivative. I get 6x minus 6, set the derivative equal to 0. That implies, in this case, x equals 1. And since we're on this curve, y equals negative x plus 2, that implies y equals 1 as well. And then we'll consider the value of the function at 1, 1, which is just 1 plus 1 minus 1, which is 1. Now we look at our second curve here. So now we do the same thing, but we're just going to substitute x minus 2 instead of negative x plus 2. So we get x squared plus x minus 2 squared minus x times x minus 2. That's x squared plus x squared minus 4x plus 4 minus x squared plus 2x. That gives us a single x squared minus 2x plus 4. So the derivative is 2x minus 2. Set that derivative equal to 0, and we get x equals 1. But for this line, if x is 1, that implies y is negative 1. And f of 1, negative 1 gives us what? 1 plus 1 minus a negative 1. So that's plus 1 again. So that gives us 3. Well, let's consider curve 3. That's the easy case, I would say. X equals 0. So if we plug x equals 0 into the function, we just get y squared. So this is a function of y. Its derivative is 2y. And set that derivative equal to 0, and we get y equals 0. And we already have that x equals 0. So what did we get? Well, we actually got the same critical point that we had before. Now, this is coincidental. You will not always get your critical points on the boundaries. That's just a happenstance for this problem, but it can happen. So just keep that in mind. Okay, so now we've looked at our 3 curves, but we're not actually done here because if you recall from Calculus 1, that when you look at a curve in 2 dimensions, you may use those critical points to find a minimum or maximum within the interval, but it doesn't tell you anything about the edges of the interval. And the same applies here, but here the edges of our intervals are these actual points. So we have to check each of those individually. So first we'll check f of 0, 2, which gives us 0 plus 4 minus 0, so that's 4. Then we'll check f of 2, 0, which gives us 4 plus 0 minus 0, so that's 4. And then we'll check f of 0, negative 2. And that's going to give us 0 plus 4 minus 0, so that's 4. So in other words, 4 is the absolute maximum. And 1, or 0 actually, was the absolute minimum. Okay, well, we made it. That's the end of this section. Thanks for staying here and watching the whole thing, and have a great day.